Hello everyone, welcome back to part 2 of lecture 17. So, we were discussing about the different parameters that influence or hinders the utilization of microwave remote sensing data in flood studies. So, let us continue that. So, let us talk about the soil moisture. So, here you can see the higher soil moisture content increases soil permittivity and radar backscattering. This enhances contrast between flooded and non-flooded areas, especially in moist soil. Wet soil can create complex backscattered signature within a single radar resolution cell, which may complicate the detection of small or mixed water bodies. So, this is one of the limitation when you are having the high soil moisture in the surrounding. Accurate modeling requires detailed knowledge of soil moisture content distribution. So, post event we can have all these measurements, and if we have continuous measurement pre and post event, then this utilization of microwave remote sensing will be very effective. Then comes the topography. So, the topography causes geometric or the image deformation and radiometric distortion in SAR images, commonly known as foreshortening, layover or shadowing, right. Shadowing can create false flood alarms as area in shadow reflects very low backscattered value, which will mimic the dark and smooth water surfaces, right. So, because of the shadow zone, we will be confused whether it is a water or whether it is a shadow. Mapping shadow zones with the local incidence angle greater than 45 can minimize misclassification of flooded areas. So, there are different papers which have reported this one. So, here you can see the foreshortening, layover and shadowing example. So, these are one of the limitation of utilizing the microwave remote sensing in flood studies. Then comes the vegetation, and we have understood the different scattering mechanism. So, you need to refer those concepts here, and then you will be able to understand how these scatterings are happening and how to utilize these to correct your information. Flooded vegetation enhances radar backscattered through dihedral scattering, which is coming from water surface and vertical elements like tree trunks, unlike bare soil where water typically reduces backscatter, right. So, here because of these tree trunk and the vertical structures, you will have more information because of the dihedral scattering. So, the signal will get modified and you will have brighter pixels. The radar returns is highly dependent on vegetation type or structure and radar system parameters like frequency, polarization, incident angle. The vegetation structure like height, density, biomass critically influences wave interaction and backscattering. This is what is explained here, right. So, in agriculture crops, increasing water depth initially enhances double bounce. However, beyond a certain depth, emergent vegetation is too sparse to maintain this effect, causing reduced backscattering, right. Now, again there will be confusion. For mature crop or dense canopy, vegetation scattering dominates and flood presence become hard to detect, right, because here we are talking about the saturation. Thus, radar sensitivity to water under vegetation depends heavily on ground stage, plant structure and water level. Here, optical detection occurs during intermediate water level with partial submergence. You can see the partial submergence, right. Then we will see how the urban structures are confusing the whole estimation. So, the radar imaging in urban setting is complex, especially with low spatial resolution, because if the spatial resolution is low, the whole building or this two buildings will be in 1 pixel. In such situation, it will be very hard to detect. High backscattering from dihedral reflection, which is ground and building walls, results in very bright radar signals. Additionally, effects such as layover from rooftop and shadow behind building further complicate the signal interpretation. Mutual shadowing, multiple scattering effects, triple bounce, reflection from windows, gable roofs, these will together cause the multiple scattering, right, between building in dense urban settlement, reduces flood detection reliability. So, even you are using the microwave data, you will not be able to prove the efficacy or the accuracy of your result. Different backscatter mechanism for various surface cover under non-flood and flooded condition. So, here you can see there is first condition when you have bare soil and grasses, then you have the next one when you have forest, and the C here is the urban. So, this is the non-flooded condition. Here you can see the water is not saturated, normal soil moisture will be present and the surface is visible in urban areas also, right. In the forest also it is visible. When we have the flood condition, so here the specular reflection will start working and then this area will be partially submerged with the water, right. And here in the urban area also this is happening. So, this because of the double reflection or the double bounce reflection, it will be hard to detect or the signal will get modified, and it was supposed to come with the dark pixel, but it will be brighter pixel, right. So, different scattering mechanisms are responsible here with different types of structure. I hope you have understood this particular concept. Backscattering intensity over grass and bare soil land cover under non-flood and flooded condition, which is represented here. So, this is non-flood SAR intensity and flood SAR intensity, right. So, these images are post flood and these are without flood, right. So, under non-flooded condition, these surfaces generally exhibit moderate backscatter due to surface roughness. When flooded, the smooth water surface causes specular reflection, reducing the radar signal return. As a result, SAR backscatter intensity significantly decreases over flooded grass and bare soil areas, right. Now, with the sparse built up areas, how the remote sensing data set appears. So, this is again the non-flood SAR intensity, this is post event. So, here you can see the sparse urban areas have a mix of open spaces and built structure, leading to moderate backscatter under normal condition. So, this is normal condition. When flooded, partially submerged building shows an increase in backscatter from double bounce scattering, right. So, here you can see this is the double bounce. Here the intensity variation is more noticeable than improving the flood detectability, right. Now, when we have the dense urban area, how it appears. So, here you can see this is normal condition, this is the flood condition. So, in non-flooded condition, building or man-made structures cause strong radar reflection, especially via double bounce mechanism. During flooded condition, backscattering may remain unchanged if water does not affect radar geometry, right. Hence, dense urban environment obscure the presence of flood water, making intensity based detection less reliable. So, here it will be very hard in the dense urban area to utilize the microwave remote sensing data in flood studies. Now, let us see the interferometric synthetic aperture radar INSAR. Each SAR image pixel contain a complex signal giving amplitude and phase information of the target. So, the amplitude, it says the strength of backscattering electromagnetic wave, and the phase is basically the last fraction of two ways travel distance, right, minus pi to plus pi. A complex SAR signal Z for a SAR pixel with amplitude A and phase is given by this equation, right. In SAR processing utilizes two SAR images over the same area with similar viewing geometry, but from two slightly different look angles to measure geometric properties of the earth surface. That is what we have when we talk about the in-SAR configuration, right. So, an interferogram is generated by cross multiplying pixel by pixel the first SAR image with the complex conjugate of the second, right. So, the interferogram can be formed with this. Here the interferometric phase and the interferometric coherence, these two will be calculated, right. I hope you remember the microwave remote sensing lectures. So, then you will be able to utilize those concepts here. Coherence or correlation is a measure of the similarity between two radar signals captured over the same area at different times, right. So, it quantifies how similar SAR signals are both in amplitude and phase, and here we will have the value range between 0 to 1. 0 means no similarity, completely decorrelated signal, and 1 means perfect similarity, fully coherent signal, right. So, here you have the example of water, vegetation and exposed lava. So, this decorrelation due to various factors that affect the similarity between two SAR images acquired at different times. The first one is the temporal decorrelation, right, then spatial decorrelation and then volume decorrelation. So, when we talk about this temporal decorrelation, it happens due to change on the ground between two SAR acquisitions such as vegetation growth, human activities or water level. So, it could be flood. It is caused by difference in the viewing geometry, the baseline, because we are talking about the two measurement of the same area from two different position, but the baseline will be same, right. So, the volume decorrelation, it occurs due to inconsistent phase information as the radar signal penetrates the canopy scattering from different depths. So, that will come from volume decorrelation. Coherence can also drop due to other reasons like widespread rainfall, making it essential to analyze overall and normalized coherence trends, right. Water bodies can be recognized as areas with low coherence between two SAR images, distinguishing them from land area that typically exhibit higher coherence, right. Further, flooded areas show reduced coherence due to surface changes, allowing maximum flood extent detection even if water is not present in both images, right. So, we are talking about the in-SAR. Pre-event and co-event coherence map are generally used to detect flood related changes, where a drop in coherence greater than 0.3 is often used as a threshold to classify a pixel as flooded and non-flooded areas, right. So, here we are using this coherence image and the threshold will be greater than 0.3. Vegetated and the fast changing terrain can also cause low coherence, which may complicate this analysis. Coherence helps to separate vegetation from bare soil, reducing reliance on optical or land cover data to detect vegetation. It also helps in differentiating increased backscatter from water beneath vegetation linked to double bounce scattering from that causes by bare soil moisture, which shows significantly lower coherence. Further, combining backscatter intensity and interferometric coherence enables clearer separation of flooded vegetation from non-flooded areas, improving map reliability. However, in case of dense vegetation, coherence is generally low due to temporal decorrelation caused by factors like wind or plant growth, making it ineffective for detecting changes associated with flood water. So, when we use the INSAR, we have to be very careful why this coherence image is coming, why these values are coming, that we need to understand and answer. Flood mapping using intensity assumes reduced backscatter in the flooded areas and increased double bounce intensity for partially flooded buildings. However, SAR intensity data alone may misrepresent flooding in complex urban setting because of the scattering mechanism due to orientation and multiple scattering in urban areas. Built up areas usually show stable coherence due to their structure stability over time because they are not changing very frequently. Hence, a decrease in coherence around structures indicate potential flooding in the area because the structures are not changing every day, right, and there will be slight modification in the structure. But because of that, if you are having the coherence values which is coming in this particular areas, then it could be because of the flooding. The urban area remains temporarily stable unless vegetation is present, and therefore, INSAR coherence is used to complement intensity, capturing both amplitude and phase correlation between image pairs, right. So, when we have the grass and bare soil land, then how the microwave remote sensing data set appears. So, this is the normal condition, right, this is the flood condition, right. So, grass covered areas may exhibit moderate to low coherence even in non-flooded condition because of vegetation movement. Flooding in grassy areas reduces coherence as water causes temporal decorrelation and changes the scattering mechanism. This difference helps to distinguish between vegetation type and flood presence when combined with SAR intensity. When we have the sparse built up areas, so here this is the normal condition, this is the flood condition. Sparse built up area usually display moderate to high coherence in non-flooded condition due to relatively stable man-made structures. During flooded condition, coherence significantly decreases as per flood water depth, building orientation and surface changes, right. Flood detection becomes more effective when coherence loss aligns with known built up zones are utilized together. For the dense urban area, this is the normal condition, this is the flood condition, and here you have the coherence value, right. Dense urban area typically show consistently high coherence in non-flooded scenario. In flooded condition, coherence often remains high or with minimal loss, making flood detection using coherence alone less effective in such areas. Combining coherence with SAR intensity or phase information is essential for reliable flood detection in densely urban areas, right. Limitation of coherence based flood mapping. INSAR faces challenges over open water due to specular reflection and surface roughening, which cause a complete loss of temporal coherence, making interferometric analysis difficult or impossible. Further, temporal and spatial baseline affect coherence, with the temporal baseline influencing the detection of flooded vegetation and the spatial baseline being more critical in urban flood mapping. High coherence persists in built up areas even during flood due to dominant point like scatterer, masking water presence, making analysis difficult. Further, radar imaging in urban setting is complex, especially with low spatial resolution where multiple scatters are within the same pixel, right. Now, the combining SAR intensity and coherence for flood mapping. So, we continue that one. Intensity based method assuming fresh water enhance backscatter by double bounce, but complex urban area or dense vegetation disrupt this effect, making such approaches unreliable. Coherence only flood detection method suffers from low spatial resolution of coherence map, limiting their precision in identifying small or detailed features. Combining SAR intensity with SAR coherence, which helps to overcome these limitations. So, here we will be having the both technique, and here we will be able to identify the regions affected by flooding using two criteria. So, the first one is a drop in coherence between pre and co-event image, then we have a change in backscatter intensity, right. So, now we will try to understand the flood mapping technique through the microwave remote sensing. So, SAR enables spatial mapping of flood affected water bodies. Flood extent derived from SAR can be overlaid on existing data sets for damage assessment, which helps in disaster response planning and resource allocation. Then flood mapping is performed using the following technique. The first one is visual interpretation and digitization. Then we have manual thresholding, then automatic global thresholding, change detection based flood indices, right. So, the visual interpretation and digitization, these will not be recorded. So, here you can see the spatial temporal flood map of Kerala obtained from Sentinel Well image and an automated OTSU thresholding algorithm, right. So, here you can see the permanent water body and the flooded areas with the green and red colors. This particular slide has all the references which I have been using in this particular lecture. So, you can refer to them if you need more information about these topics. So, you will have more information on this particular aspect. Thank you very much.